Hey everyone, and welcome to The Explainer. Today we're diving into a material you probably see, maybe even use, every single day: cast iron. We think we know it, right? It's heavy, it's strong, it makes an amazing skillet. But hidden inside this ancient metal is this fascinating secret, and it's all about carbon. So what is the real story of cast iron?
It is literally everywhere you look. From your car's engine block to pipes, manhole covers, all sorts of heavy machinery. But here's the thing that's kind of weird. For a material that we think of as super strong, it's also famously brittle. You can't really bend it or hammer it into a new shape like you can with steel. So what is going on inside of it? What gives it this really unique personality?
Well, to really get cast iron, you first have to meet its more famous sibling, steel. You see, they're both from the same family. They're both iron-carbon alloys. But a tiny, tiny difference in their recipe makes them behave in completely opposite ways.
And here it is, laid out plain and simple. The dividing line is right around 2% carbon. If you're below that, you've got steel. It's flexible, it's ductile, you can shape it. But the moment you go above 2% carbon, boom, you get cast iron. Hard, brittle, but way cheaper to produce. It's kind of amazing that just a little shift in that one ingredient creates two materials with completely different destinies.
This is the magic number. More than 2%. That's your ticket into the cast iron club. But, and this is a really big but, just having enough carbon isn't the whole story, not even close. The real magic is in what that carbon does once it's inside the iron.
And that quote really nails it. It's not just about the ingredients, it's about the recipe. How you cook it, the way cast iron is made, especially how it's cooled, and what other little things are in the mix. That's what unlocks its true potential, and its biggest secret.
So let's get right to the heart of it. The real secret of cast iron isn't a number, it's a shape. It's all about the physical form that the carbon takes as the metal cools down from a molten liquid into a solid. So, okay, we know it has over 2% carbon. Check, we've established that. But that's just the starting point. The real question is, what happens to all of those carbon atoms? Where do they go?
This is it. This is the whole shebang. The crucial point is, does that carbon get chemically locked up with the iron, or does it basically decide to go its own way and separate out? That single choice determines everything about the final material you get.
And there's a name for this process: gravitation. You can think of it like a battle happening inside the cooling metal. Will the carbon form a super hard, brittle compound called iron carbide or cementite, or will it precipitate out as soft, slippery flakes of pure graphite? Yeah, the same stuff that's in your pencil lead.
So how do engineers actually control this? Well, they have two main dials they can turn. The first one is the cooling rate. If you cool it down really fast, you trap the carbon as that hard cementite. But if you cool it slowly, you give the carbon atoms time to find each other and form graphite. The second dial is silicon. Adding silicon to the mix actually encourages graphitization. It actively pushes the carbon out to form on its own.
And by playing with these two dials, cooling rate and silicon content, metallurgists can create a whole family of different cast irons. Each one has its own unique structure and its own personality. So let's meet the four main characters in this family.
First up, white iron. This is what you get when you turn both of those graphitization dials to off. You cool it fast, and you keep the silicon content low. All the carbon gets locked up as cementite. There's no free graphite at all. The result, a material that is incredibly hard and wear-resistant, but, you guessed it, super brittle. It's perfect for things that need to grind and crush, like the lining inside a rock crusher.
Now, let's flip the script and do the complete opposite. By cooling slowly and adding plenty of silicon, you get gray iron. This time, all that extra carbon has time to form into little flakes of graphite scattered all through the metal. These flakes make the iron really easy to machine and fantastic at absorbing vibrations, which is exactly why it's perfect for engine blocks. But the downside is, those sharp flakes act like tiny little internal cracks, which is what makes it brittle.
But what if you could have the best of both worlds? That's where malleable iron comes in. And this is a pretty brilliant trick. You actually start with that hard, brittle white iron. Then, you put it through a really long, slow heat treatment. It's called annealing. Over many, many hours at a super high temperature, the hard cementite breaks down, and the carbon reforms into these small rounded clumps. And that new shape makes the iron much, much tougher and more ductile.
And that brings us to the modern marvel, ductile iron. This was a huge breakthrough back in the 1940s. By adding just a tiny bit of magnesium or cerium to the molten iron, metallurgists figured out how to make the graphite form into perfect little spheres, or nodules, right as it cools. See, these spheres don't create stress points like the sharp flakes in gray iron do, and that allows the metal to be both strong and ductile. It was an absolute game changer.
So we have our four main types, right? And they're all defined by the shape of their carbon. But modern metallurgy, of course, goes even further. They fine-tune the properties with a whole bunch of other elements.
You can think of these as the fine-tuning knobs. After you've set the big dials, you can use elements like sulfur and manganese to hold back graphitization and make the iron harder. Phosphorus can add wear resistance. And for really tough jobs, you can add things like chromium and nickel to create special cast irons that can stand up to extreme heat and corrosion.
And this family portrait just sums it all up perfectly. It shows you the trade-offs. White iron gives you that incredible hardness, but you pay a big price in ductility. Gray iron is a dream to machine, but look at ductile iron. It's the real standout, scoring high marks in almost every single category. That combination of hardness, ductility, and castability is exactly why it was, and still is, such a revolutionary material.
So, the next time you pick up a cast iron skillet, or you walk over a manhole cover, just remember, the secret isn't really the iron. It's the carbon inside. It's the shape it takes, flakes, spheres, or being locked away, that truly defines its strength, its character, and its whole purpose in our world.